So today I'll be starting on the last chapter on which is inorganic chemistry, chapter study pack 13, nitrogen and sulfur. Last week we discussed in detail the chemistry of group 7 or group 17, and with this lesson we'll be completing the inorganic chemistry. So this nitrogen and sulfur, we're studying about the chemistry of nitrogen and manufacture of ammonia in the Haber process, and sulfur and sulfuric acid, the details of it. I hope all of you have got the hard copy of this study pack. To begin with, the study of the nitrogen. The nitrogen, as we know, about 78% to 79% of air is nitrogen. Now, if you analyze why such a high percentage of nitrogen air is nitrogen, is that the lack of reactivity of the nitrogen. Nitrogen, if you analyze the dot and cross diagram of nitrogen, you have a triple bond. Nitrogen forms a triple bond with another nitrogen atom, so which makes nitrogen unreactive. Triple bond makes it nitrogen almost unreactive. It's not an inert gas, but it's very unreactive gas because it's very hard to break this triple bond. Only the lightning activity can break the triple bond, right? So during lightning, yes, it breaks, triple bond breaks, and also in the exhaust pipe, the vehicle exhaust system, and inside the vehicle engine, in fact, the nitrogen bond is broken, and the vehicle exhaust system releases nitrogen dioxide gas as a result of the reaction between nitrogen and oxygen, because inside the vehicle, for the combustion, air is taken in, not oxygen. The air is taken in because air contains nearly 80% of nitrogen. So what happens is that nitrogen triple bond is broken inside the engine because of the high temperature, and that is made to react with the oxygen, and that's how the oxides of nitrogen is produced as a result of the vehicle exhaust. So this because this higher percentage of nitrogen in the air, we can extract the nitrogen from air for various industrial processes, like the manufacture of ammonia in the Haber process, or the manufacture of fertilizers, explosives such as trinitrotoluene (TNT), and also nitric acid. So the air, if first of all, is taken in, and it is cooled and compressed until it turns into a liquid. Air is first turned into a liquid, cooled and compressed until it turns into a liquid. Then this is until air turns into a liquid. First of all, you take air in and you remove the water, you dry the air, and then you remove the dust particle by filtering the air, and you convert the air into a liquid. And then you liquid air, you slightly, then this is liquid air, it turns to about minus 200 degrees Celsius. And when it heated up to minus 196, you can obtain liquid nitrogen. You can obtain liquid nitrogen. When it is further slightly heated to minus 186, you get liquid argon. When you heat up to minus 183, you get liquid oxygen. So liquid nitrogen at 196, liquid oxygen at 183, and liquid argon at 186 degrees Celsius. This is the fractional distillation of liquid air. So nitrogen industrially is obtained by the fractional distillation of liquid air, right? So this nitrogen is a colorless, odorless, no color, no smell, tasteless gas, slightly soluble in water, and that is very unreactive, as I explained before, right? So please copy this. Air turns into a liquid air, and then it is slightly warmed to obtain liquid nitrogen. This lack of reactivity of nitrogen is due to the presence of the triple bond. So nitrogen exists as a diatomic molecule N2, triple bond between the nitrogen atoms. So this triple bond makes the nitrogen, fairly unreactive, and there's a very high bond strength, very hard to break the triple bond. In fact, the bond enthalpy of the nitrogen triple bond is about 945 kilojoules per mole, right? In fact, the bond energy of nitrogen is more than the bond energy required to break the oxygen or hydrogen. That's the reason why nearly 79% of nitrogen, or 79% of air, is nitrogen. Please copy the dot and cross diagram and the Lewis structure of nitrogen. Okay. Right. So nitrogen has a very low temperature. Liquid nitrogen is about minus 196 degrees Celsius. So therefore, liquid nitrogen can be used to freeze fruits which cannot be frozen under the normal conditions, right? It can be used to freeze fruits which cannot be frozen under the normal conditions. And like for example, strawberries and dry coffee. And it is unreactive gas, therefore, it can be also used to pack certain food items in order to prevent the bacterial decay, because in absence of air or oxygen, the bacteria will not survive. So therefore, as a food storage method, you can store food in nitrogen. Yes, there's a question, advantage of having more nitrogen in air. That makes our air almost unreactive, because if not, there'll be a problem. Because sometimes you might imagine why nitrogen is 80%, why not oxygen being 80%? Because oxygen we need so much, right? So why in nature nitrogen is such a high percentage? Imagine if oxygen is 80%, we will not be able to put off any fire, right? Because it will be, the whole globe can catch fire within few hours, so that's very dangerous. So the atmosphere, it's very important that the atmosphere is not very reactive. So that's the reason why in the nature, in 80% of air is nitrogen. So that's the advantage. Other than the above mentioned uses of nitrogen in protecting food, nitrogen can be also used in the manufacture of ammonia. We'll be discussing how nitrogen can react with hydrogen to form ammonia. That is the basis of the fertilizer industry, right? Basis of the fertilizer industry, because ammonia is very important and can be used as a fertilizer. Ammonium salts like ammonium nitrate, which is a common fertilizer known as nitram, or ammonium phosphate, ammonium sulfate. Various ammonium salts are used as fertilizers because nitrogen is a very important element for the plant growth and for the crop yield, to increase crop yield and for increase plant growth. Ammonia is important, nitrogen is important, as also the ammonium salts can dissolve easily in water and break it into ammonium ion, so the roots of the trees or the plants can easily take ammonia up their roots. And also nitrogen is used in the manufacture of the nitric acid. It is used in the manufacture of nitric acid. Nitric acid, HNO3, is made by the reaction of nitrogen dioxide with ammonia, and also a manufacture of nylon and explosives such as TNT. TNT stands for trinitrotoluene. So that for that we use the nitrogen. Manufacture of nylon. We'll be studying how to make nylon in the under polymerization, under organic chemistry, and the manufacture of nitric acid. We use nitrogen. And also, if you need any inert atmosphere in the reaction vessels, we can use argon atmosphere, or even nitrogen can be used. It's much cheaper to use nitrogen, because argon, if you analyze in the atmosphere, is about 0.9%, less than 1% is argon. So even though nitrogen is not 100% inert, you can use nitrogen in inside reaction vessels or inside the bulbs in order to give an inert atmosphere. Those are the uses of the nitrogen gas. So that happens, nitrogen gas in presence of lightning activity at high temperature inside the combustion engines, it reacts with the oxygen in air, because nitrogen triple bond can be broken at very high energy. It reacts with the oxygen in air to form nitrogen monoxide, which can further react with oxygen and form nitrogen dioxide. Can further react with oxygen and form nitrogen dioxide. Right. So that is how nitrogen dioxide is added to the atmosphere. Right. Please copy this. So one of the main element of ammonia is nitrogen. Nitrogen is a base. If you analyze why nitrogen is acting as a base, because the ammonia in nitrogen acting as a base, because nitrogen has a lone pair of electrons. So this lone pair of electrons on nitrogen can accept H plus proton, can accept a proton and form the ammonium ion. Because we know, as to the Bronston-Lowry theory, which we have discussed under the chemical equilibrium, any substance which accepts protons, proton acceptors are bases, proton donors are acids, and proton acceptors are bases. So nitrogen in ammonia has a lone pair, so that can accept H plus and form the ammonium ion. This is the reason why ammonium salts are basic. Ammonia itself is acting as a base, right? And also these ammonium salts can easily react with bases to form ammonia gas. I think we have discussed this under test for cations and anions as well. Let me show you how ammonium salt, any ammonium salt, we take ammonium, say for example chloride, reacting with any strong alkali, this produces ammonia gas. And in fact, this particular reaction can be used as a test for ammonia gas. You add sodium hydroxide or any strong alkali. You add sodium hydroxide or any strong alkali, and then you hold moist red litmus. Red litmus is used to test for the alkali gas. You hold moist red litmus. What happens is that the red litmus turns blue, indicating the formation of the ammonia gas. This is how the ammonia gas is produced in the laboratory, and that's how it is tested by the. You have the ammonium. Right. I hope the video was clear. Sorry, I was muted. Was the video clear? There's no video. Okay, I'll play it again. Sorry, this is a nitrate one. You take any ammonium salt to a boiling tube. Usually we use boiling tube, even though this is a test tube. You're heating, and then you add any strong alkali, and then you warm. Ammonia gas will be evolved. Ammonia gas will be evolved. You can test the gas with moist red litmus. It turns blue because ammonia is an alkali gas. Right, okay. That's the test for the ammonia. So ammonia acts as a weak base, accepting H+ ions from forming a dative bond with a lone pair of nitrogen and extra hydrogen ion easily removed again from the ammonium. And ammonium salts react readily with bases to produce ammonia gas. You can copy this reaction. There's a question. I'll into that question. Why nitrogen needs a lot of energy to break its bonding? Sorry, break if its boiling point is minus 196. That question you need to know in comes to simple covalent molecules. Simple covalent molecules, the boiling and melting points are determined by the strength of the intermolecular attraction, not the strength of the bond. We have discussed this under intermolecular forces under the chemical bonding chapter. So the boiling and melting points of simple covalent molecules are determined by the strength of the intermolecular attractions, is not the bond. But in giant covalent structures like diamond graphite, you need to break the bond in order to boil or melt the covalent substance. It's giant covalent structures like diamond graphite, because they don't exist as molecules, they have giant continuous structures. But if you take ionic compound like ionic bonding, then ionic compounds, they exist as crystal lattice structures. They exist as crystal lattice structures. In that case, you have to break the bond. So you need to give a lot of energy if it is an ionic substance. Ionic substance, you need to give a lot of energy because you need to break the strong bond, which is the ionic bond.